Hello everyone, my name is Sanjeeb Thapa. I am a PhD student at the University of Kansas and my advisor is Dr. David Darwin. My research is on bond behavior of epoxy-coated reinforcing bars in non-proprietary ultra-high performance concrete. In this presentation, I will introduce ultra-high performance concrete, commonly called UHPC. I will talk about objectives and scope of my research, and then I'll explain my research and findings. So what is ultra-high performance concrete? It is an advanced construction material which has very high compressive strength, often greater than 20 KSI, and it has high tensile strength, greater than 1 KSI. It has 1 to 3% by volume of steel fibers, and most commonly used volume is 2%. And it contains no coarse aggregate. It has low water to cementitious material ratio, generally less than 0.22, and it is very workable. It has a spread of 8 to 10 inch. So how to measure spread of UHPC? As shown in the picture, a spread cone is taken and it is filled with UHPC. Then the spread cone is lifted and UHPC is allowed to flow. After that, you will measure the diameter of the spread in two directions, and the average diameter is recorded as the spread of UHPC. Advantage of UHPC. Why we need UHPC? It has very high compressive strength and the fiber performance which allow for the development of reinforcing steel in very short embedment length. Therefore, it makes it as a viable option for use in bridge deck closure strips which can be made very narrow. You can see UHPC is being poured in the bridge deck closure strip, and you can see the bridge deck closure strip are too narrow. So why we need this research? Most UHPC mixtures are proprietary, which makes them too expensive. They are around 20 times more expensive than conventional concrete. And the existing design approaches for bond strength in UHPC are based on pullout test. These pullout tests are not recommended for determining bond strength because the test setup used in this type of test will confine the concrete around the test bar, which result in higher bond strength than the actual one. So the objective of our research are to develop non-proprietary UHPC using locally available materials, especially Oklahoma Department of Transportation approved materials, because this research was funded by Oklahoma Department of Transportation, and to perform realistic bond test for use in design, and finally develop a design recommendation for splice length in non-proprietary ultra-high performance concrete. So in this research, we prepared 144 UHPC batches. We performed 92 modified pull-out tests. We tested 24 modified beam specimens and 28 beam slice specimens. We evaluated 3 bar size, number 4, number 5, and number 8 bars, as they are the most commonly used bars in bridge deck. We have not gone more size than number 8 because they are not used in the bridge deck. And we evaluated 3 bar types, uncoated, epoxy-coated, and textured-epoxy-coated bars. Due to time constraint, I will skip modified beam test and modified pull-out test from this presentation. I will explain beam splice test in detail, as that test was the basis for designing our design recommendations. Uncoated bars. So, as we all know, uncoated bars are most commonly used in reinforced concrete, but they are more likely to have corrosion. So there comes epoxy-coated bars, which has a protective coating and prevents the corrosion. However, it reduces the bond strength between the concrete and bars. So the engineer comes up with a new solution. It is a newly available bar in market, which is called textured epoxy-coated bars. It is believed to offer the bond strength equivalent to uncoated bar and corrosion protection at least of epoxy-coated bars. So win-win situation on both ends. We are evaluating this newly available bar as well in our test. The first task of our test was to develop non-proprietary ultra-high performance concrete using Oklahoma Department of Transportation approved materials, which include type I cement, slag cement, silica fume, sand from Oklahoma, although we have sand in Kansas, but it was funded by Oklahoma, so we are obliged to use the sand from Oklahoma, and different super plasticizers. We prepared 90 trial batches using different material proportions, water to cementitious material ratio ranging from 0.171 to 0.22, and different superplasticizers. Out of those batches, we select 2 mix which has better compressive strength and good spread, and we label them as mix A and mix B in this table. You can see both mixes have same water to cementitious material ratio of 0.183. Mix A has spread of 10.13 inch, while mix B has spread of 9.75 inch. In terms of fiber distribution, mix B has well distributed fiber distribution compared to mix A, and it was observed by evaluation. Like we took batch from different portion and see the fiber distribution inside the mix, and we also cut the cylinders into 2 halves and see how the fibers are distributed. And each of these mix had 2 superplasticizers from the same company. In addition, mix B had also a set oscillator. Talking about compressive and flexural strength, mix A and mix B exhibit almost similar compressive strength. You can see mix A achieved 9.56 KSI compressive strength at 1 day and 14.95 KSI compressive strength at 7 days, while mix B achieved 8.57 KSI compressive strength at 1 day and 14.40 KSI compressive strength at 7 days. In terms of flexural strength, mix B has higher flexural strength compared to mix A. Mix B achieved 2.98 KSI flexural strength at 3 days and 3.60 KSI flexural strength at 7 days, while mix A achieved 2.78 KSI flexural strength at 7 days. You can clearly see mix B has 29% higher flexural strength compared to mix A at 7 days. I am focusing more on 7 days because we achieved 14 KSI strength at 7 days, and all our splice tests, which I will discuss later, were performed at that age. And mix B being achieving higher flexural strength is more likely because it has well distributed fiber distribution compared to mix A. Therefore, we select mix B for further evaluation in our beam splice test. Talking about our bone test, all our tests were non-contact splices, and there is a code provision for non-contact splices that the clear spacing between the bars, splice bars, must be limited to 1/5 of the splice length or 6 inch, whichever is smaller. But we did not meet this requirement in our test, and our test results later, which I will explain, will show that this requirement is not needed in ultra high performance concrete. So our splice test consists of 2 precast concrete side panels connected together or spliced together with ultra high performance concrete. As shown in this picture, you can see 2 precast concrete panels being spliced with UHPC, and these precast side panels were cast with conventional concrete. The key variables investigated in the splice test are bar size, bar type, splice length, bar spacing, and concrete cover. So we investigated 3 bar size, number 4, number 5, and number 8. Similarly, we investigated 3 bar type, uncoated, epoxy-coated, and textured-epoxy-coated bars. The splice length also has ranged from 6 dB to 10 dB, where dB stands for diameter of the test bar. Bar spacing refers to center bar spacing between the splice bar, and it ranged from 1.5 to 3 inch. Likewise, the specimen had concrete cover of either 1 inch or 2.5 inch. So we use 4-point bending test for our splice test, which is most commonly used for the lap splice investigation. And you can see here the splice region is placed in the constant moment region, and load is applied at 2 inch using hydraulic jacks, and the applied load were measured using load cell placed on the hydraulic jacks. You can see the smiling face in our helpers or student hour workers because the test was successful and they were smiling. So this is the splice test result for uncoated, number 4, number 5, and number 8 bars. You can see the plot shows the bar force at failure in keeps versus the product of splice length LS and C prime sub B. C prime sub B refers to the cover to the center of the bar being developed to the nearest concrete surface. You can see it does not include bar spacing because from our test result we observed that the minimum of the concrete cover governs rather than the bar spacing. So in this plot, you can see the red one represents number 4, blue number 5, and green number 8. So to identify or investigate the trend in our test data, we performed a dummy variable analysis. So the dummy variable analysis is based on the assumption that for bars of different sizes, the change in product of splice length and cover has same incremental effect in bar forces for all bar sizes. However, the absolute value of bar force can be different for each bar sizes for the same value of product of splice length and cover. And you can see from the dummy variable analysis, we obtained 3 best fit fine lines for number 4, number 5, and number 8 bars, which are represented at number 4 trend line, number 5 trend line, and number 8 trend line in the plot. And here you can see bar forces increases in linear but not in proportional fashion with the product of splice length and cover. Also, larger size bars exhibit higher bond force, higher bar force compared to smaller bar size for the same value of product of splice length and cover. We performed similar analysis with epoxy coated bars, and you can see we observed similar type of results for even epoxy coated bars also. And we compared our test results with the bar stress in conventional concrete using ACI 48 database for contact splices without confining reinforcement having the same compressive strength. And when we compared our test bar stress with the ACI calculated bar stress, we found that the ratio of FS test to FS ACI 48 has a mean of 2.23 for uncoated bars, 1.94 for epoxy coated bars, and 2.37 for textured epoxy coated bars. So in general, the bond strength or bar stress in UHPC is 2 times compared to that of conventional concrete. Also, you can see the ratio of epoxy coated to uncoated bars has a mean of 0.87, which is higher compared to conventional concrete, in which the ratio is less than 0.7. So we developed a design equation based on our splice test results, and this is the proposed design equation for splice length of reinforcing bars in non-proprietary ultra-high performance concrete, which depends on bar size, yield stress of bar, bar coated factor, and cover. You can see the bar coated factor is 1.0 for uncoated and textured epoxy coated bars, as they exhibit equivalent bond strength or bar stress in UHPC, and it is 0.7 for epoxy coated bars. We solved this equation for Fy and treated as FS design. Then we compared that FS design with our test results, and we found that the ratio of FS test to FS design for uncoated bars has ranged from 1.60 to 1.03 with a mean of 1.26, standard deviation of 0.172, and coefficient of variation of 0.136. Likewise, for epoxy coated bars, the ratio ranged from 1.71 to 1.00 with a mean of 1.32, standard deviation of 0.193, and coefficient of variation of 0.146. For textured epoxy coated bars, the ratio ranged from 1.62 to 0.96 with a mean of 1.32, standard deviation of 0.289, and coefficient of variation of 0.218. So this comparison shows that our proposed design equation is satisfactory, as we have a decent coefficient of variation. In summary, UHPC can be made from locally available materials which we made in our lab. Admixtures play a big role in UHPC because admixtures will impact the flow properties of the UHPC and even the fiber distribution, which has direct impact in our bond strength. And bond strength in UHPC is 2 times that of conventional concrete without confining reinforcement at the same compressive strength. The negative effect of epoxy coating are less in ultra-high performance concrete compared to conventional concrete. And finally, textured epoxy coated bars have the same bond strength as uncoated bars. Thank you for your patience, and I am happy to answer your questions.